So we have another 10 to 15 minutes. I'll just continue on stress, right? So when we're talking about strain, we saw there was different ways of measuring strain. You could use the deformation tensor, B and C, Eulerian Lagrangian. You could use the strain tensor, Eulerian strain tensor, Lagrange. And similarly, when you describe stress, there are different measures of stress as well. Where you choose whatever is more convenient or whatever is more consistent as well from the point of view of the mathematics and the physics behind it. So the Cauchy stress, that's also called the true stress by engineers for some reason. That's fairly common, and that's Eulerian, right? It's telling you the force per unit area in the deformed configuration. But to every Eulerian quantity, there's a counterpart Lagrangian quantity, and that's what we're going to do here. It's getting a bit dark. I'm just going to switch the light on. Just bear with me for a sec. Yeah, that's better. Okay, so yeah, I'm going to introduce what's called the nominal stress tensor. Well, I'm just going to recall Nelson's formula. Which gives you the link between the area of a surface element in the reference configuration and its counterpart in the current configuration. So it's like this, Ft and dA, the other way around. Formula. Okay, so if I look at the traction force, that's T and dA, and we saw, so that's the force, right? It's Tn is per unit area, but if I multiply by dA, I get the force. With Cauchy's theorem, we saw that there was sigma n dA, and then with Nelson's formula, I see that I can write it like this. And dA. And so I see that I have a tensor in front of NdA, where now NdA is the area and the normal in the reference configuration. So I can write it as follows. Oops. Equals, I can write as something T, yeah, I'm gonna write like this, J and dA. Is that really the same? Yes, because I remember that the transpose of AB, it swaps the order in the multiplication of tensors. So if I do the transpose of f minus 1 sigma, I'm going to get sigma t f minus 1 t. Right? So the traction force is S T and dA, where I've just introduced this S is J F minus 1 sigma. That's the so-called nominal stress. And the engineers call that the engineering stress, or sometimes it's the transpose of that they call the engineering stress. We can only call it the nominal stress tensor, right? So, and that measures the same force, right? T and dA, that's the force applied on the element area. So the sigma measures the force per unit reference, current area, and S measures the force per unit reference area. Or I guess I should say per unit area in the current configuration, per unit area in the reference configuration. Right. Notice that's very important. S is not symmetric in general. Because F is not symmetric in general. If F was symmetric, then F minus 1 would be symmetric. S sigma is being symmetric, that would make S symmetric. So in special cases, S can be symmetric. In general, the nominal stress is not symmetric. So in that respect is not as nice as sigma. In another aspect is much more amenable to measures, right? Typically, when you do what's called the tensile test, which is what mechanical engineers do all day, every day, right? In anywhere I go, you will find that the workshops in the Alice Perry building are full of tensile machines there. But typically, that's what you do. You take a sample. So, like I said, like a cylinder or a strip or just a bar, and then you have a machine apply a tensile force, uniaxial uniform stress, like this, and then the machine, a tensile machine, that's what it's called. Sometimes you do compression, right? If you have concrete or rocks, hard to pull on them, so it's easier to push on them. But most of the time you're testing, metals, or in our case, you'll be testing rubber or biological tissues. So the machine measures T, the force. It just basically applies just a crunch, a system of pulley that pulls on it, and there's a load cell that tells you how many newtons are being applied at the moment of deformation, right? As a function of L, right? It measures L as well, the length of the material, of the sample. So either you track the distance between the two clamps, or else you could glue little speckle little mirrors, one apart away from the other on that. Right? Maybe here you're going to glue a little mirror, and here another little mirror, and then you shine a laser beam, and the beam is going to be reflected just at those 2 points, and then you can have a machine that's going to just track the distance between those 2 points. Either way, you're able to measure T, the force in newtons, and L, the distance in meters, right? And then you collect this data, you have a spreadsheet, and then you just divide by little l by capital L, the original length, and that gives you lambda. And in that way, you have access to the strain. And then if you divide T the force by the area. And now that's a bit trickier because area by area, I mean the cross-section area here. That's going to give you the tensile stress, the Cauchy stress. Right, but little a is going to change as the material elongates. The cross section is going to shrink, and then you're in a bind here because you also have to track little a, which means tracking the cross section length, the depth and the height, and that's much harder. Whereas if you were to just track T and then divide by the original cross section, that you do that before you do the test, you measure the size of the sample, and you have S, and that gives you direct access to the nominal stress. Yeah, we're gonna say, but A track. And this is much easier to compute because you measure the cross sections once and for all. You have capital A, and then you just track T, the force, and you have direct access to the nominal stress. And of course, ultimately, it's all equivalent, right? You can just move from one to the other. And I guess now with machines, it's very easy to link that to a computer program that will do that for. In the early days, they were putting weights and then measuring the distance. It was much harder to do those measurements, and so they were sticking with the nominal stress. But like I said, one is equivalent to the other. To those transformations, A minus 1 Fs. Nominal stress, Cauchy stress, Linear Lagrangian. Okay, and just like I was able to write the equation of static equilibrium as div of sigma equal 0 in the current configuration, I should be able to write their counterpart in the reference configuration, the Lagrangian formulation, right? So I just recall here what was the equation of static equilibrium. And that was simply that all the forces, surface forces, will balance out in the current configuration. And so I can just rewrite this in terms of S, right? Sigma T, so it's going to be J minus 1 MdA. And then the transpose of a product of tensors is the product of the transpose, but in the reverse order. It's going to be ST, FT, NdA. And then here I notice that I have Nonsens formula, right? That's going to be the same as ST J minus 1 T NdA, and here that's Nonsens formula. Sorry, I was a little n. I just mixed up two steps here. Right, so I've just brought the J minus 1 to the right of ST, and now in that bracketed term, I recognize Nonsens formula. gives me NDA. And so now I'm still integrating over a surface, but now the surface elements are D capital A. So now I'm in fact doing the integration in the reference configuration. And now I can use the divergence theorem in the reference configuration, or that's going to be div S dv. But div with capital D is the divergence theorem, the divergence operator with respect to capital X, the coordinates in the reference configuration. And this must be 0. This was for any region, a sub-region, and so on and so forth. And so I can conclude that this equation of static equilibrium read as follows: divergence of S equals 0. So that's very nice, right? Okay, I'll just write it here. Lagrangian formulation. Whereas the Eulerian formulation gives us sigma involves the divergence, the Eulerian divergence, and the Cauchy stress tensor. So these are equivalent. Sometimes one is more convenient than the other. And that also justifies the introduction of that tensor as the nominal stress tensor. Like I said, you could also have this transpose that's called engineering stress. And then you can have all sorts of other stresses. And if you read in the books, you will see that other measures of stress are introduced. Just like that, an infinity of measures of strain, there's an infinity of measures of stress. We're just going to focus on those two in this course, just telling you that you might encounter others in other exposition of this material. Okay.